We're going to continue our theme of looking at this aluminum cyclic test data that we've had from a variety of now situations, and this time we're going to turn to this what we call goodness of fit, which is all about a test, a hypothesis test related to the underlying distribution. Now, way back when we first presented this data in the module 6 in the summary statistics section, we called this a probability plot. Some people would really call it a quantile plot because it is related to the standardized normal variate as opposed to putting probability on this vertical axis. And I mentioned at that time that this linear regression line that we see here is going to tell us something about what's happening with fitting a line to this data, and on this particular plot, something that fits like a line would say that that is a closer and closer to the appropriate underlying distribution. And this correlation coefficient being so high told us something as well. That was a little bit of a hand-waving kind of argument back then, and these probability plots don't give us necessarily a direct quantitative way to and reliable, consistent way to accept or reject that particular underlying model. We're going to get into how to determine what these lines look like in Module 11 when we get in the linear regression topic of the course. For now, though, we're just going to leave this aside and say, hey, look, this is one way to do it. We're trying to get to this notion of an underlying distribution, and although we're going to focus on the normal distribution, there's nothing that restricts us to that. Right? And so for a hypothesis testing kind of standpoint, what we're going to end up looking at in this goodness of fit test is a test statistic that looks a lot like our variance statistic, where the differences here are going to be what we're going to put in the numerator and in the denominator of our sum, and we're going to look at deviations that are squared, and then we're going to normalize by that. Right, now, what these are observed frequencies versus what we call the expected frequencies. And before we get into defining this too much, this sum goes from 1 to k, where k equals the number of bins or classes in our histogram. So frequency meaning just like we talked about with the frequency histogram. Here's one that we used back yonder, so to speak, with an interval of 200 in the bins, and that was just a pure frequency histogram. So k is our number of bins, and we end up having this as a chi-squared distribution, where we're going to end up with k minus p minus 1 degrees of freedom. So because our statistic that we're going to do is observed frequencies within a bin, that's why the I is running from 1 to k, and why we start with a k as our degree of freedom, subtract off 1 for having used the data, and then minus p. P is because that's the number of parameters in the distribution used, or I should say estimated, by sample statistics. So for the normal distribution, which has of course two parameters, mu and sigma, we'll estimate mu with x bar, and we'll estimate sigma with s. So that's going to mean that p would equal 2 for the normal distribution. Okay, so it's probably best illustrated here by taking a look at an example. And so the the kinds of tabulation that we'll do are seen down here in this table that are associated with this particular frequency histogram. At the end of the day, though, what we're going to be doing is comparing the test statistic with our chi-squared value that goes along with a particular alpha and our k minus p minus 1 degrees of freedom that go along with that. Right? And so for this particular set, then if we want a 5% statistically significant conclusion, and then we have 70 data points, and we've used then we've estimated 2 parameters, so that's 2, so k minus 2 minus 1 will give us 67 degrees of freedom. Okay. So let's look at what we've got in this table and the way that it's worked. Here's our bin widths from 0 to 900, 900 to 1100, so on and so forth. So 200 for the bin widths. This last one stops at 2300 because the max is up in there, and this lower one goes from 0 to 900, and because I lumped this one here along with this one there because we want the number of observed frequencies to be at least 3, preferably 4 or 5, and that's why I went ahead and lumped that and reduced the number of classes down. Up here we could have done that for these top two as well, but I chose not to. Somewhat arbitrary there, I guess. The other part was that there was a gap here in that bin, so that was another good reason just to go ahead and push that on up into the other one. Okay, so here are the observed frequencies in those specific bins, right? And this right here is an intermediate calculation column, right? This is theoretically what we would get from the probability of seeing the data from 0 to 900 in that region, and then theoretically from 900 to 1100. And the way that we got that is, you see the z sub u and z sub I there. The z sub u is associated with the upper bin, and z sub I is associated with the lower bin, and where the z is just calculated by the bin minus the mean divided by the standard deviation. I'm sorry, that's x minus the mean divided by the standard deviation to give us then the z values, and then we just do your typical normal calculation. So that gives us this area, this frequency, this proportion, relative frequency in that bin, and then you're just multiplying this by your total number in your sample. So that's a fraction of the sample, really like a population kind of fraction, times n. That gives you, that would be 70 in this case, and that gives you the 7.4. So that's how we get these expected frequencies for that particular bin. And then here, this is the compilation of our individual squared or chi values for each bin. Okay, and then just add them all up, and that gives us our sum. That gives us our statistic for that data set. Okay, so then we got to compare that to our criteria value. and that comes back up here, the chi-squared at 0.05 significance level, 67 degrees of freedom, and reading out of the tables, having to do a little interpolation, we'll get about 87. I mean, so now the question is, oh, well, what matters here, right? And so we're going to reject the hypothesis. Our decision rule is we reject H null if our test statistic is greater than our criterion value. Right, that's the fixed significance approach. Right, and in this case, 3.3 is not greater than 87, so we fail to have convincing evidence that H naught is wrong. Right? And, well, gee, what was H naught? Well, that was sort of implicit here that, gee, we were testing to see that the underlying distribution is normal. And so really what we've seen is consistent with that this data set is consistent with that. The other way that you could potentially do this is go and take a look at a calculated p-value. Right? And the p-value here is the probability that our k minus p minus 1, this is now our criterion value is greater than chi-squared. And in this case, that is a fairly large number. And we find out that that is greater than 0.995 for that value being, or sorry, for this being equal to 5.4, and our number is even less than that, so this number is actually a little bit larger, and that doesn't really tell us a whole lot from a p-value standpoint. Large p-values don't particularly help us a whole lot in terms of if we're looking to reject the null hypothesis. So in other words, this is all just another way of suggesting that the distribution is, that the evidence certainly cannot rule out that the underlying distribution is normal. It's about what we expect. And we saw that from the probability plot as well. Now another way to run this would have been to, instead of doing those equal width bins, instead to run it so that the expected frequency is the same in each of the bins. And we do that by, if we go back to our underlying distribution and say, okay, we'll take, and this is a little bit arbitrary, but 8 classes. And that's what we got here, 1 through 8. 1, 2, 3, 4, 5, 6, 7. You say, well, right, that's 7 boundaries, but it gives us 8 classes. Right, and so there's our eight classes there. So we divvy that up. The z value then is really in fractions of 8. You go and you find the corresponding cumulative normal. Yikes. Boy. By the time you get the handout, this will be fixed. So, production team, stop! And we're going to go back. I'm going to fix that and quit stumbling around on this page. Me right there, T. So one way we did that was with equal width class bins, and we don't have to do it that way. And sometimes actually, in more conventionally, we actually end up with equal expected relative frequencies. That's what we're really after here. And the way that we do that is by, for instance, with our normal distribution, we're going to break this up into 8 equal bins. A little bit arbitrary, but that's the same number of bins that we had in the first example as well. And so we'll divvy up the cumulative frequency, or cumulative relative frequency, that is, probability, by 8s. Okay, and so now the z value that corresponds with that is listed here, and of course with a symmetric around 1/2, as in symmetric with respect to the cumulative here, then we've got minus z is equal to positive z, so to speak, right? And when we reclassify then the observed frequency, we get a different kind of histogram. We get unequal widths. This is plotted with as though they are equal, but they're not. That's because this is Excel, and this particular kind of chart is going to, by default, give you equal width. So this is not an arithmetic scale down here. But that's all right, because it just illustrates the up and down kind of nature that's going on. And it doesn't seem like we're going to have a great normal fit, but it's just not the same kind of histogram anymore than what we saw before. So don't get thrown off too much by the shape there. Right, and so here's our new bin widths down here. Here's the observed frequencies in that area. And then here's our expected frequencies. Note that we get that expected frequency by taking the the values that we had up here multiplied by capital N. And that gives us then the same expected frequency in each one of these. And so this is actually kind of an interesting, useful way of doing it, because now you can look at observed frequencies and see directly and easily how far are they apart. It's easy now to look at each and every bin in terms of comparing them from one to the other, whether or not they should or shouldn't, because of course the normal distribution is up and down, the hilltop, right? And so as you go equal widths in terms of these numbers out here, well, you shouldn't get the same frequency, right? But if we just convert it to having the same expected frequency that changes the widths over here, and makes the numbers actually a little simpler, more straightforward to do the calculation. No big deal when you're using software these days, but in the old days that would have been a bigger deal. And the same kind of thing here. Here's the summation of the statistic that we're after. There's our final number, and that's of course much less than what we had before of 87. So we end up with the same conclusion at the end of the day for this particular one, but the test statistic has a slightly different numerical value. Crappy, to be honest, but